Here's a video on using an op-amp as a comparator. And when you use an op-amp as a comparator, there is no feedback. So there's no connection between the output and either of the inputs. And as I mentioned in one of the first videos about op-amps, when you have no feedback like this, the output of the op-amp is just the open loop gain times the difference of the voltage that's on your input. So just the difference of the voltage on the non-inverting input that I have labeled VP and the voltage on the inverting input that I have labeled VN. Remember, this plus V and minus V, these are just the power sources that are powering the transistor circuitry that's inside the op-amp. Now, very important point is that when you don't have any feedback, there is no longer a virtual short at the input of the op-amp. And the reason why you no longer have a virtual short is because the difference in voltage across the inputs is no longer zero. Okay, that wouldn't make sense, because if it was zero, then this term here would always be zero and it wouldn't be much use. So when there is no feedback with an op-amp, you will have a difference in voltage across the inputs, and that difference in voltage is right here. Now, even though the voltage across the inputs is no longer zero, the current ideally at the inputs is still zero. So even a comparator with no feedback still has the ideal current value of zero at each of its inputs. Okay? Alright, well, now to see how a comparator works, we're just going to recall a couple of things. First of all, recall that the open loop gain, okay, this constant A, the ideal value of open loop gain is infinity. And then also remember that V0 has to be within the rails. Okay, again, the rails are the power source values, plus V and minus V. So with these two conditions here, along with this equation, we can determine, well, what the possible outputs of a comparator are. So first, let's take the condition that if the voltage on the non-inverting input, VP, is greater than the voltage on the inverting input, VN. Well, what we would have here is V0 would just be infinity times a positive number. Okay, disregard that little tick mark there, that was a mistake. And when you have infinity times a positive number, well, that's going to be plus infinity. So you see, V out, under this condition where VP is greater than VN, V out wants to be the most positive it could be. You know, it wants to be out to positive infinity. But because V out can't be outside of the rails, when V out tries to be positive infinity, it's going to hit this upper limit, okay, this upper rail limit. So what's going to happen is that when VP is greater than VN, V out is just going to equal the positive source amount, okay, the positive voltage supply. All right, well, if you have the opposite case, if we have VN greater than VP, well, now V out will be infinity times a negative number, okay, since VN is greater than VP. So here it wants to be minus infinity, so it wants to be as negative as possible. And what happens is it hits the lower rail, and V out equals the minus source value. So you see, a comparator just has two possible outputs, either the plus power source value plus V, or the minus power source value minus V. Now, a question that often comes up is that, you know, students will ask, well, what if VP equals VN? You know, like they're exactly equal. Well, mathematically, V out's just going to be infinity times 0. And if you remember in your mouth, that's undetermined. Okay, so that's, the theoretical answer. Now, in practice, and those of you that have taken a lab have seen this firsthand, is that it's very difficult in practice to get two voltages to exactly equal each other for any significant amount of time. What will happen when two voltages are close in value is that they'll just hover, and VP will be slightly greater than Vn, and a little while later, VP will be slightly less than Vn, and these values, they just hover each other. So in a case like that, if these two input voltages are very close together and they're both hovering, going back and forth, where one moment one's greater than the other and the next moment the other one's greater than the other, well, what happens with V out is that it starts oscillating between plus V and minus V. And this becomes an unstable point. And depending on how the comparator is being used and what sort of application, that instability in the output voltage, when these input voltages are close together, it can be a problem sometimes. It can be very undesirable. But then in other applications, that instability in V out due to the input voltages being close together, well, it may not be a problem. So it's just application oriented whether that unstable V out is a problem or not. And in some future videos, we'll talk about applications where it is desirable, and that, or applications where it doesn't matter, and then applications where you don't want that instability, and there's something you can do in a case like that to make it more stable that we'll talk about.